In the last lesson, we looked at determining the pH of weak acid and weak base solutions. What we're going to look at today are the solutions of salt acting as weak acids and bases. Now this, at this moment, might seem a little bit bizarre because your experience with salts to this date is based on the Arrhenius definition of acids and bases. As you know, Arrhenius states that an acid-base reaction is one where an acid plus a base makes salt and water. We've stated before that with the Arrhenius definition, it applies mostly to strong acids and bases. And what you'll see is that salts that are formed from strong acids and bases will not affect the pH, but salts that are formed from weak acids and bases will affect the pH. So what we're going to look at is how to decide whether or not a salt will be acidic or basic in water. And then we'll look at how we can calculate the pH using an ice chart and the appropriate Ka or Kb. Okay, so as you know, hydrolysis is the reaction of a substance in water. So something like the acetate ion, and we have the salt sodium acetate, it reacts with water and acts as a base to produce hydroxide. And this is acetic acid or vinegar. Okay, it's conjugate. The ammonium ion, if it's on its own in solution, so say for example I dissolve ammonium chloride, when it hydrolyzes with water, it produces NH3 and H3O+, making this ion acidic. These examples are just showing the actual acidic or basic ion. But what we're going to actually end up starting with is the salt. So we're going to have that metal, non-metal, or metal and polyatomic ionic compound. And we're going to look at how we use its behavior in water to decide whether it's going to be an acid or a base. Now the key here, when you're looking at something like ammonium chloride, which is a salt, because it consists of a cation and an anion, we have to recognize that this will dissociate completely in water. So that's always going to be our first step, is to look at how the salt itself on its own behaves in water. And as you learned in the solutions unit last year, if something is considered soluble in water, it will dissociate completely to produce the ions, in this case NH4+ and Cl-. Now what we need to do is look at these two ions and decide whether they can be acidic or basic in water. So you'll recognize I'm dealing with NH4+ here, and as you saw above, the NH4+ can behave as an acid. Okay, so it reacts with water, donates a proton to water to produce NH3 and H3O+. Now, we need to discuss the chloride here and discuss why it doesn't act as a base. And we always need to look, when we're dealing with salts, we always need to look to the conjugates of the substances we're dealing with. So for Cl-, okay, its conjugate is hydrochloric acid. And its Ka value, because it's a strong acid, is going to be very, very high. Okay? So for example, let's just give it a value of 10 to the 10 as an example. Now, in order to determine what the Kb of the chloride ion is, we need to use our relationship Ka times Kb is equal to Kw. Okay. Now you know that Kw is 1 times 10 to the minus 14. So when we look at this, if we know the Ka for our acid, its conjugate, in this case, is going to be 10 to the negative 24. Okay, because 10 to the 10 times 10 to the negative 24 gives us 10 to the negative 14. So what we see here, based on this relationship of Ka times Kb is equal to Kw, the stronger the Ka value, okay, the larger the Ka value, and thus the stronger the acid, the weaker the conjugate base will be. So because HCl is a strong acid, its conjugate is going to be significantly weak, to the point where it will not really behave as a base to a measurable extent in water. In the case of NH4+, its conjugate is actually NH3, which is a weak base. So when you have a conjugate that comes from a weak base or a weak acid, it will actually have the ability to affect the pH. So in this case, the NH3 has a Kb value of 1.8 times 10 to the negative 8. And if we calculate, what we see is that the Ka for NH4 is actually 5.56 times 10 to the negative 10. So you can see this is much, much larger, and it will actually have a measurable effect. Okay, so it's basic enough to have an effect where we can actually measure the quantity of H3O plus in the solution. Okay, so this relationship that you learned in the last lesson is critical to understanding whether or not an ion is going to affect the pH of the solution. Now what you're going to find is that if you can rule out ions that don't affect the pH and you're left with a cation, the cations act as weak acids, okay? And anions tend to act as weak bases. Okay, so let's look at sodium acetate. So this is a salt, so it consists of a cation and an anion to produce Na plus and the acetate ion in solution. Now from our strong bases, okay, sodium hydroxide is one of our strong bases, so we know that it will not affect the pH. This is the conjugate of acetic acid, which is a weak acid, so we know that this will be a base and it will be able to affect the pH in the solution. So I write the hydrolysis reactions, the acetate ion plus water, okay, producing acetic acid and hydroxide. So the anion will be a base in solution. And if we look at an example of something like sodium chloride, which is where your experience lies, we've got Na plus and Cl minus. Neither of these affect the pH, and that's why we can say that this will be a neutral solution. Now, in a case where both ions hydrolyze, so both ions are weak or strong acids, it's about their relative Kb and Kas. So if the Kb is larger than the Ka, the solution will end up being basic. If the Kb is smaller than the Ka, the solution will be acidic. And if the Kb is approximately equal to the Ka, the solution will be close to neutral. Now, this here, this kind of a situation is one where we won't deal with in terms of calculations. You may be asked to predict whether it's basic, acidic, or neutral just based on the relative Ka and Kb values. Okay, we're going to discuss the salts containing these in class using a diagram. Okay, but for now, what you can just kind of look at is that if you've got one of these ions in solution, so this is another list that you sort of need to memorize, okay, the pH will actually be less than 7. And we'll go over that in class with a diagram. Okay, this summarizes the situation that we have in terms of deciding whether a salt is going to produce an acidic, basic, or neutral solution. So let's look at some examples here. We want to predict whether the following solution will be acidic, basic, or nearly neutral. Okay, looking at it now, I see that I've given you the exact same example. So what I'm going to do is actually give you a different example here. I'm going to give you CH3 NH3 Br. Okay, so this is a salt, okay, that consists of a cation and an anion. So what we need to do to decide if it's an acid, base, or a neutral solution is we need to break it up into its ions. Okay, so what we have here is CH3 NH3 plus plus Br minus. Okay, we need to look at these ions, okay, and decide if either one of them comes from our list of strong acids and bases, or is the conjugate of one of our strong acids and bases. Okay, so our strong acids, okay, are HNO3, HCl, HBr, okay, HI, HClO4, H2SO4. Okay, so anytime you have an ion, that's a conjugate of one of these. So in this case, the conjugate of HBr, okay, we know that it won't affect the pH. It'll still be in the solution, but it won't affect the pH. Okay, and then this one here is a cation, so I know that it's an acid. Okay. Also, if you look at your table of Kb values, you'll find the CH3NH2, and that will help you to recognize that this is the conjugate. CH3NH2 is a base, so therefore its conjugate must be an acid. Okay, so this salt here dissociates to produce Na plus and Cn minus. So Na plus comes from our list of strong bases. So the key here is to be able to recognize whether you've got a strong acid or base conjugate. Okay, so lithium, sodium, potassium, rubidium, calcium, strontium, barium. Okay, these, when they are ions and are combined with hydroxide, are strong bases. So they end up really being spectators, okay, in a salt reaction. So this is a spectator. It does not affect the pH at all. Cn minus is an anion, so we know that it's a base. It also has no hydroxide, so it's a base in solution. Now with the NH4 plus NH4Cn, when this breaks up in solution, oops, okay, we get NH4 plus and Cn minus. When we look at our list of strong acids and our ions that form bases, there's no conjugate here, so we know that both of these have the potential to affect the pH. So what we look at are their relative Ka and Kb values. So the Ka for this is 5.6 times 10 to the negative 10, okay? And the Kb for this one is 2.0 times 10 to the negative 6. Now the way that I determined that, in the table in your notes, you actually have those ions because it gives you the conjugates as well as the Kb's and Kas. But if, for example, you were given only the NH3 Kb, you would need to use Ka times Kb equals Kw to figure out the K for this. Okay, and the same scenario for this one. I can find that the Kb is this by using its conjugate, Ka, from HCN. Okay, so in this case, the Kb is larger than the Ka. So essentially it's a competition, and that's going to mean that we're going to end up producing more hydroxide ions than we would hydronium ions. And what decides whether a solution is an acid or a base is the relative quantities of the hydroxide and hydronium ions. So we've got one more example to do, and this is going to be a multi-step problem that's going to help us to find the pH of a salt solution. So we've got the pH of NH4Cl that we're looking for. So NH4Cl, okay, when you recognize that you've got a salt, so it may say that you've got a salt, Or another way that you'll know that you're dealing with a salt, or a clue that you're dealing with a salt, is that you've got one of the conjugates of a strong acid or base. You want to look at the formula and try to recognize that. The other way that you can tell that you've got a salt is that you might be given the Kb in the question or the Ka in the question that doesn't match the formula that you're given. So for example, you might be given that the Kb, okay, for NH3 is 1.8 times 10 to the negative 5. I believe. Okay, so when you look at this, you're asked for the pH, it gives you this solution, and then it gives you a Kb that doesn't match. Okay, that's a really good clue that this is potentially a salt, and we need to examine it further. Okay, so the first step, okay, is to dissociate the salt. So I'm going to write a little list of steps here. Okay, so we're going to break it up into its ions. And the decision-making process that you did in example 1 needs to happen here. So we need to decide that Cl minus does not affect the pH, but the NH4 plus does because it comes from the weak base. And at this point as well, you can see NH4 plus, you are given the Kb for the conjugate. Okay, so that's yet another clue to you that you're dealing with a salt that affects the pH. Okay, so once you've dissociated the salts, you need to decide, okay, the acid-base ions. Okay, so we've decided that this is an acid. Okay. Then what we need to do is set up an ice chart, okay, of that ion that affects the pH. So NH4 plus affects the pH, so we need to write its hydrolysis reaction. So it's reaction in water. We've decided it's an acid, so it's going to donate a proton to the water, and we're going to be left with NH3 and H3O plus. And at this point, it's becoming more like a regular problem. So one main difference with a salt is that you need to do this dissociation of the salt and decision making about the ions. Once you've decided which ion is acid or base, setting up the ice chart is more straightforward. One other difference, okay, is that you're not going to be given the Kb or Ka value that you actually need directly in the question. Okay, you need to use your relationship Ka times Kb is equal to Kw. So you were given the Kb is of NH3, and we're dealing with NH4 plus. So what we need to do is actually solve for the appropriate Ka value. So in this case, Ka is equal to 5.6 times 10 to the negative 10. Okay, and that's equal to x squared over 0.155. I can make the assumption because that's very, very small. I can now solve for x. It's 9.317 times 10 to the negative 6. And I can then find the pH directly. And I find that it's 5.031. Okay, so if you follow these steps when you're dealing with a salt, okay, it will guide you through, keeping in mind the key differences are step 1, 2, and 4. Setting up the ice chart and solving our standard. At this stage, you can complete the practice exercises in the textbook, and you're also prepared to do AcidBase on line 3, which asks you to solve problems of calculating pH of weak acid, base, and salt solutions.